Well, let's get rolling. Thank you very much for joining our webinar on the MSA. Let me introduce myself. My name is Jaroslav Staněk, and my responsibility in Diribet is to make sure that the technical things will not get disconnected from the mathematics, and vice versa. And let me introduce you my colleague, Martin Motička. He's also online. He's visible with his webcam. And he'll be taking care of your comments and questions you may have. Please use the Zoom capability of Q&A for asking questions, and you are welcome. And I see you are already using the chat tool that we have available. This webinar is the first one in a series on the measurement system analysis, and we decided to make it small, make it short. We'll have about 20 to 30 minutes each. It is a big topic in small pieces. You all have the possibility of unmuting yourself. So if you please, you are welcome to make yourself heard to everyone and ask questions in live if you are not comfortable with the Q&A or chat. Very good. We've decided to make this as a breakfast. I know it's not breakfast for all of you, but it's breakfast time here. So the obvious first questions, you also have polls. So I'll open the first poll. What do you like with your morning coffee? Please start your voting. I see the votes are turning in. We don't have everyone yet. Okay, we are over 50%. Over 50% of votes turned in, so let's see what it looks like. And these are the results. Okay, so Krausland, but obvious choice, MNX the most. I'm afraid these are wrong answers. You don't have it right. The right answer is to have a MSA for breakfast, or you can have some combination of the traditional breakfast like aloo puri with experiment type 1, or pancakes with experiment type 2 if you don't like the pure measurement system analysis. But I see we have, well, not over 50%, but yeah, seems like pretty good result. Thank you very much. So let's get back to our topics now. I'll give you just a short overview of the topics that we plan for the upcoming webinars. You will of course have those in your email, and we'll be meeting every second Friday in the month. And in the third Friday of each month, we'll have this webinar in the Czech language, if that is of an interest to you. All right, so to the first topic. Before we'll enter to the characterization of the individual terms that we use in this regard. The first obvious question which needs to be asked is what is MSA and what is it good for? The MSA stands for Measurement System Analysis, as all of you know, and its purpose is to try to answer the question if the measurement device is fit, generally speaking, fit for the purpose it's used for. And one of the leading principles here is that every measurement system is wrong. Every measurement system is uncertain. And with that, I'll have to give you another poll. And that is, are you surprised with the statement that every measurement device is inaccurate? Please start your voting. %27% voted. We need to have some more. Let's make the quorum 50%. We need 50% of votes. 63%. Okay. Okay, we have over 70% of polls in. Let me end it then, and I'll share the results. Well, we had 1/3 of the attendees saying that they are surprised by the statement that every measurement is inaccurate. Okay, so this is a thing that we generally need to address. So very well. Are there any questions or any comments on this in the chat, Martin?
No, we have nothing here.
All right. Okay, so this is something. This principle is very important. If there is a measurement device, the natural thing to perceive about the measurement is that we can make it ever more accurate. If we have a wooden rule and we want, it is not enough accuracy for the purpose that we have, we should go for more precise measurement device, maybe the steel rule or something like that. And this was the notion for the antique age and all of the Middle Ages, that people who measure actually observe that they are wrong time to time, and that this being wrong can be eliminated in some way by being more precise, by having better measurement equipment, or by praying more, or doing something that would eliminate the error. Nevertheless, just after the Middle Ages, in the Renaissance age, when measurement or the metrology itself became very popular in connection to astronomy, it became very unuseful to get this approach. And rather than thinking of the result of the measurement of something that can be corrected, it became more useful to think of what may be the error in the end. So rather than saying the planet is over there under this angle at this time, it became more useful to say the planet is between here and there. And of course, the more precise observation it was, the narrower the interval was. Arguably, it is more useful to have a small confidence bounds on the observation, but the confidence bound was always there. We didn't have a precise enough of an instrument to bring it down to zero. And this became so popular and practical that it is actually useful to think of every measurement as having an error. This is more of a paradigm. This is more of a abstract thinking exercise than the physical world that we have. In metrology, we tend to make the analogy that there is some precise value of the thing that we measure, and that is unknown, but it is there. And we measure it, we enumerate it with a limited precision. And that's the Renaissance principle. That's the Renaissance principle, and that is the principle that we will be using here in the measurement uncertainty. Nevertheless, in the 20th century, with the dawn of modern physics, and particularly the particle physics, it turns out that this principle is brought another step further. Not only that we assume there is an uncertainty around the, let's say, real value, or we assume there is some real value, the particle physics does not assume that at all. The particle, this types of thinking around the world actually brings the uncertainty principle to another level by not assuming that the reality is even there. And generally, the idea is that the reality is caused by the observation. Not that it is that important for us. We are not that modern, we are not that cool. We stick with the Renaissance principle of assuming that there is an error. Well, we may come to a conclusion that our error is very close to zero. Like, for example, counting the number of people in a room. Let's say there are 3. So we count 1, 2, 3, and we don't need to actually say it's 3 plus minus 0.1. The counting 3 people is good enough if we have a good definition on what does it mean being in the room and what does it mean a person. So there are some special cases, even in practical metrology in the industry, where we assume a zero error on measurement, particularly on counting, but that very much depends on the definition. Okay, so for the sake of our discussion and for the sake of this webinar, we'll assume there is an error, and if there is none, we would conclude that by estimating the error to be 0. Very good. So there was an opening comment on the actual existence of uncertainty, and if you don't agree, please write it to the to either Q&A or chat. Okay. On the industrial scale, we of course need to have some easy to do approach how to address this. And specifically in the industry, the purpose of the measuring device, we need that to assess the fitness of the measuring device. The purpose is the production process control. We assume that the data from the measuring device are used for some type of a decision, and we need to make sure that they are adequate for the decision. And that decision specifically would be the control intervention. We would be looking into whether the measurement is good for control intervention. And traditionally, there are two approaches in that. I'm calling them here the American and the European. The first one comes from very much a common sense approach to measuring devices. There is a measuring device, you come to it and you have some parts to be measured, and you measure it repeatedly and see if the values are similar. And then you take two different parts, measure them, you know they are different, and you expect different results. Or you take several people, ask them to measure the part that you have measured before, and you expect the measuring device to produce similar numbers again. And this first approach is just making these common sense experiments, probably everyone would do with a measuring device, and formalizing their evaluation. If I say the results need to be similar, then I would come with a criteria how similar they should be. If I have different parts and I want the results to be different, then I would come with a criteria on what this different means. And contrary to that is what I would call a European approach, and that is not doing these simple experiments, but rather studying the measurement device from inside, looking deep into it, looking into what is the principle of measurement, what are the things that are being used, how the measured value is transferred to the display of the measuring device, and studying this chain. And this is called the study of uncertainty. And the purpose is to find what is the nature of the uncertainty which is in the end, to build it up, bottom up, rather than the other way around. Well, the American approach has the advantage that it is rather simple and easy to use on an industrial scale. The disadvantage, on the other hand, is that it only is able to reflect the individual demonstrations of the uncertainty. On the other hand, the European approach has that. It combines everything into the final result, but it is extremely impractical, and it was not used almost at all, even though we have standards for that already. Well, and several years ago, about 5 or so, there was an initiative to bring these two together and to come up with what I would call a reasonable approach. And it is to utilize the easy experiments, utilize the easy American approach, but not to evaluate it individually, but combine all of these experiments into a common evaluation, which would reflect in a good enough shape the overall measurement uncertainty. And that's the reasonable approach. And this is exactly what we'll be speaking about. Okay, so how is this done? Let me see, how many of you have done an MSA study? I'm launching a poll. Please submit your responses. It's coming up. We have over 50% already. We have almost 80%. I'll end the polling then. Here are the results. Time to time, most of you. Never, a third of you. Regularly, 20%, that's very good. And 10% only when the auditor is at the door. I suspect it's more than that. It seems that none of you does it on Sundays and holidays. It probably is not one of your guilty pleasures. So for those who have never done the MSA, the third of you, let me show you the basic principle. And we'll be going over this in our webinars. So I'll give you just the beginning. As I've said, we are specifically trying to study the fitness of the measuring device. This is the measuring device, operation 30, in a production line. What do you see here? That's a production line consisting of several operations, and we have a metrologist here. We have a person who is responsible for making sure that measuring devices are good enough to control the production process. And that person usually has a list of all the devices in the factory and comes to them usually once a year or per the period he decides, or the system in that factory decides, and looks at the device. And if that person is inexperienced, they see the device and they have a checklist here and go step by step in this checklist to see if the device is functional at all, what type of measurement it is doing, and they start making experiments. The first experiment we will be talking about is the measurement system experiment, and it will be the next webinar. And there are several of these. So he needs to put together all of this information and evaluate it in the end. And this is the act of measurement system analysis. This is what the metrologist person does. Well, this is an experienced metrologist. The experienced one would come, and before they start checking off their checklist, they would stop and look around. What we need to have, what is the purpose, is to have a proof or making sure that we trust each of the device in the factory. But that does not mean that we need to work with all of them, or that we need to do an experiment or this checklist of experiments for each one of them. There are different combinations of that. And this is what I would like to come to specifically in this part of the webinar, that what we are actually doing is the validation act. And it is not connected specifically with a measurement device. That's something what we call a measurement system formally here. The validation act is the procedure that looks into a combination of the measurement task. The measurement task are the specific quantities on the measured part that are subject of the production process control. It may be the diameter of the getting here or the length or any of these parameters. They need to be strictly given. And that is what we call the measurement task. The other part of the puzzle is the measurement system. That's the particle measurement device that we use. It can be CMM, it can be as simple as the sliding caliper or something what we call a communal measuring device. And the third piece of the puzzle is the measurement process. That's how the measurement task will be handled on the measurement system. The measurement process usually involves people who are handling the measuring device and the parts. It is the environment in which we do that. It is the method that we use. With each measuring device, we can use more than one method of measurement. And strangely enough, it is also the part itself. We can have the same part with the same measured characteristics, so the same task, but at points of time that part may be stabilized temperature. Sometimes it can be unstabilized temperature directly from the turning mill or any production process that can make it hot, or it can be dirty, or it can be cleaned. So the measurement process also involves the measured part. Speaking about the measurement process experiment, and uncertainty will be speaking also about the deviations from the nominal form, which also is part of this measurement process and measurement process uncertainty. So this is the point I specifically wanted to come to in this come to today. And with that, let me give you some examples. In each of these webinars, we'll be finishing with how things can go wrong, what to do if it seems incapable or unqualified. And we have not measured so far anything. We have not talked about the qualification. But already there are instances where it does not fit. Like, for example, if there is a production line, very similar to the one which I've showed you before, but now you don't have one, but 5 measuring devices. How would you approach that? And let me give you a poll here. Let's say we have 6 measuring devices. What is the best to do? They are in one place of the production line. There is them for capacity reasons. They have lower capacity. The measurement has lower capacity than the production line, so we need to wait for the measurement result. So what should we do? Do 6 times the MSA for each of these gauges, or select 2 as a representative representative sample, or make 1 for all gauges at once? We only have 35% responses now. Or the last one, let's take the best one and just copy the report. We have almost 60% of votes in. Well, it's over 50, but well, it seems that it's not that easy to answer this one. I'll end the polling now. You have about 65%. And these are the results. We only have 2 out of these 4 selection points. The first one is to make 6 times the MSA for each of these gauges. That's 20%, and 80% answered make 1 MSA for all gauges at once. In my opinion, this is the right answer. Why I would say that, even though we have 5 separate measuring devices, they are used all together for the same purpose. So from the point of view of the production line, they serve as a common feedback of what is being produced. So generally speaking, we can have results from every one of these measuring devices in the end, and every one of them can produce a number and fed it to some operation which is before. So we not only need to make sure that they are individually fit for the purpose, but that they are fit as a group. And even though we are able to assess things like a bias or linearity in each one of those, we need to also make sure what are the differences in between those. So in my opinion, and the opinions may be differing on this one, but in my opinion, the best thing is to treat them as one measuring system. It's 5 measuring devices, but 1 measuring system for controlling of this production line. And the last thing which I would like to finish with is what to do in other individual situations that do not fit exactly the analogy which I have given, the combination of the measurement task, the measurement system, and the measurement process. Let's say this would be the example A. We have 1 measuring device which measures the diameter, and that is a continuous quantity. And in the same measuring device, we have a detection of cracks. And this is an attributive quantity, just okay, not okay. So what to do in this case? We have 1 measuring device for 2 very different measuring scales. So in my opinion, the most reasonable thing to do is to formally separate those to 1 and 2 measuring device and assess them separately. So contrary to what I've said before, combining several measuring devices into 1 measuring system, here I would do exactly the opposite. And that's on the basis that we have different nature of the measured quantity. Okay, another example. We have example B. We have 1 measuring system that is a sliding caliper, and it is measuring the same dimension. It is the length 30. It can be diameter or it is a length of the ellipse plus minus 2. So the length is the same and the tolerance is the same. Is it 1 validation act or 2 validation acts? Well, in this case, it is 2, because we have different part. We have different measuring task. That's one reason. The other, we have different measurement process. The faces on the round surface, on the cylindrical surface, are different from the elliptical one. And we can assume that with the sliding caliper, we'll have higher uncertainty measuring the ellipse rather than the diameter. So in this case, again, need to be separated into two validation acts. And the last example I have here, the example C. Let's say we have two diameters. They are produced by the same production process. But first, they have the tolerance of 30 plus minus 2, and second, they have the tolerance of 30 plus minus 3. Would this be two separate validation acts or just one? In this case, I would say it would be one. We only need to qualify it for the lower tolerance. And if it is qualified for the lower tolerance, that's plus minus 2, it is also good enough for the plus minus 3. And this is under the condition that they are produced the same way. So for example, the nature of the form uncertainty, the nature of the surface is the same. And this happens when a manufacturer of some part is supplying the same part to two different customers. Two different customers are having slightly different specification, but this specification does not affect the way the part is produced. The part is produced the same way for these two different customers, only the specification is slightly different. Very good. I see I'm over the time by 7 minutes now. I'm terribly sorry about that. We'll have the demonstration of how this is done in a software by Martin next time. Besides that, we will be speaking about the experiment for the measurement system assessment. That will be the second topic in this line of webinars. Well, for today, let me see. Do we have some questions on the Q&A? I don't think we have. Do we have anything in the chat?
No, there is no question here.
Very good. So since we are over the time, I would like to ask you to send us your questions by email if you have any, and next time we can discuss them. Thank you very much for your attention and enjoy your day.
Deary bet, we are deary bet. Deary bet, we are deary bet. Deary bet, we are deary bet. We are deary bet.